Okay, good evening, everyone. I hope I'm audible. If anyone can confirm.
Yes, madam.
Okay, thank you. So, do you guys have any doubt regarding the previous sessions or any particular question?
No, madam.
Okay. Okay, so welcome everyone to the live session of week 3 of Nonlinear Vibration. This course is being taught by Professor S.K. Dwivedi of IIT Guwahati, and today I'm here to take some questions which would help you to solve assignment 3. Okay, so firstly, if you would have gone through the lectures, so a professor has talked about the way of solving nonlinear equations. In the last week, he taught about the methods that may be used to get the equation of motion. But equation of motion is not enough to know what is the response of the system. So in order to know that what is the response of the system, it is important. It is important to just a second. Okay, so I'll just start. Okay, so yes. So as I was saying, that equation of motion is not the only thing which is important to know about the response of the system. So in order to know about the response of the system, it is important to take out its either closed form solution, preferably closed form solution. But in case of nonlinear system, it is very difficult to find a closed form solution. So that is why we go through the either the approximate techniques or the numerical techniques. Okay, so okay. So I'll just start by taking up the first question. Okay. So in case of approximate solution, what do? We use various methods like the direct expansion method or the Lindstedt Poincare method or the harmonic balance method in order to find the solution in an analytical form, but it's an approximate solution and maybe erroneous. Okay, so we use the numerical technique. Now, in order to use the numerical technique, as I have discussed earlier also, we use the ODE 45 of MATLAB. So you can use the RK4 method directly also, but since I want to simulate for a very long interval of time, it is important to. Is my video visible to you all? Okay, thank you.
No, madam. Still, video is not.
Okay, but my screen is visible,
Yes, yes, madam.
but you cannot see my video.
Yes, madam. Not visible video.
Okay. I'll just rejoin, okay? मेरे कैमरा में तो दिखा रहा है. मेरे आईपैड में दिखा रहा है। उन्होंने क्या बोला? एक को नहीं दिख रहा। I hope now it is visible. My screen is visible, right? You're able to see the presentation.
Yes, madam. Only screen is visible. Video is not visible, madam. Screen is there.
Okay. Let me just see. Okay, let it be. We'll continue with the presentation anyways. Okay, thank you. Okay, so yeah, so in order to solve the differential equation, as I've discussed in the earlier class as well, we can use ODE45. Okay, so either we can use it on ourselves or we can use the MATLAB. So why is the use of MATLAB? Simply because if I want to use the RK4 method manually, it will take a very long time. Okay, and human error is going to occur for a very long time of simulation. So that is why people prefer, or even I prefer, that we use some mathematical tools like MATLAB in order to simulate the system. So we use ODE45. Now in case of ODE45 or for RK4 method, what do? We use a first order differential equation in order to get its integration, right? But in case of like second order differential equation or third order differential equation, how do we proceed? So we usually change the differential equation. We try to convert the third order differential equation into three first order differential equations, right? So from there, there comes the question, for a spring mass system as shown in figure, how many first order differential equation is required to get its response from ODE45? So coming on to its equation of motion. Okay, I've discussed this question earlier also. Still, I'll go by discussing it. I'll just go in a brief way so that it will be useful and you'll just remember that how do we use the force balance method in order to find the equation of motion. So if you people remember that there are two mass, now there are two mass, two springs, x1 and x2. So this is a 2 degree of freedom system, right? X1 and x2 are independent of each other. So we'll have two governing equations, right? So for the mass m1, we have x1 here. So what are we going to have? If this is going downwards, a spring force K1 X1 is going to be applied like this. We'll have inertia force like M1 X1 double dot. Apart from that, we are going to have force due to the spring with stiffness K2 as well, which is going to be K2 and the relative displacement, which is going to be X1 minus X2. Correct? I'm not going into the depth because I've already discussed this question. Now, this was for a linear system, but this is a nonlinear system. So in case of a nonlinear system, we'll find the analogy. This is M1, this is X1. The inertia force is going to be the same, M1 X1 double dot. But this spring force is going to change. As given in the question, spring force F1 is given as like this. So it will become K1 1 X1 plus K1 2 X1 cube. Apart from that, for the spring K2, it will be taken up from here, K21 into X1 minus X2, which is the relative displacement, minus K22 X1 minus X2 cube. Correct. And similarly, if I go for the second mass, which is M2, what am I going to have? I have this displacement X2 and I have the spring force K2 X2 minus X1. Here also I'm going to have the relative effect. Apart from that, there will be a inertia force as well. to double dot. So again, if I'll take the analogy, what is going to happen? This is M2 X2, then we'll have the spring force. This is going to be replaced by the inertia force is going to be the same. Only the spring force is going to be changed because of the nonlinear spring. What is going to happen? It will be K2 X2 minus X1 minus K21 and K22 X2 minus X1 whole cube. Okay, we'll just separate it so that it will be easier. Yeah. So I'll get the equation of motion. Right. So the first equation of motion is cancel m1 x1 double dot plus k11 x1 k12 x1 cube, and then I'm going to have plus k22 x1 minus x2. Oh no, here it will be k21 k22 x1 minus x2 whole cube will be equal to 0. Okay, so this is my first equation of motion. My second equation of motion will be m2 x2 double dot plus k2. Okay, see, I have done a mistake here. Here it will be minus, isn't it? K2 1 x2 minus x1, and then there will be minus of k2 to x2 minus x1 whole cube is equals to 0. So essentially I have the equations of motion. Okay. However, after seeing the diagram itself, I can predict that there are going to be two equations of motions, right? But I have done the derivation in order to prove that, okay, there are going to be two equations of motion, because sometimes intuitively what we feel is not always correct, right? See, as in case of a pendulum, if you see, the pendulum is oscillating in the xy plane, correct? But its generalized coordinate, if we go to the generalized coordinate, if we consider only theta, it is going to have only one equation of motion, right? Though it is having two coordinates. So when we are working on a very complex system, it is important that in order to find out how many equation of motion it is going to have, we go through the derivation of the equation of motion. Okay, then only we are going to have the perfect answer. However, if you have practiced a lot, then you can intuitively say that, okay, this is going to be the number of equation of motions. Now, since I've got the equation of motion, as the question says that how many first order differential equation do I require? So see, both the equations of motion have the second differential of the x1 and x2. Correct. Now, in order to find x1 and x2, I have to integrate twice. From here, I can get the expression of x1 double dot. From here, I can get the expression of x2 double dot. And if I'll integrate twice, then only I'm going to get the response of the system x1 and x2. Correct. Now, this is a nonlinear system, so I cannot do it analytically. I mean, obviously, we can try, but it's a very difficult process, right? Even if we use approximate techniques, it is going to take a lot of time and lot of calculations, and it may still result into erroneous results. Okay, so in that case, I'll use ODE45. So I'll have to convert it into first order differential equation. So if I come to equation number 1, also there is one thing that should be seen, that in the first equation and second equation, the coupling is only between x1 and x2. Okay. In the first equation, there is no term of x2 double dot, correct? And in the second equation, there is no term of x1 double dot, correct? If it happens, then we'll have to decouple the equation in order to solve it with ODE 45, but that is not the case. Okay, so what I'll do, I'll first convert this into two equations, right? I'll define Z1 as I'll define Z1 as x1. Then if I'll define Z2 as Z1 dot, which is equals to x1 dot. Isn't it? Is it fine? This way I'll just give the expression of Z dot and I'll get the corresponding value. Now again I'll define Z3 as x2 and I'll define Z4 as Z3 dot, which is also equal to Z2 dot. Correct? So now if I want to define Z dot, what is going to be the expression? If I'll see, it is going to be an array with, I'll write in terms of x, okay, for the understanding. I'll have x1 dot, x1 double dot, then I'll have x2 dot and x2 double dot. Okay, I'll have to give four initial conditions and I have to give four equations. So I've converted these two equations into four first order differential equations. Okay, so the answer of this question will be 4. I hope that it is clear to everyone what I have done. Nothing, I have acceleration. Okay, I have the second differential. I have broken it into two parts. First, I'll take the first differential and then I'll take the second differential. So I'll have two equations for the first equation, two first order equations. For the second equation as well, in the same way, I'll have two first order equations. So in total, I'll have four first order differential equations. And those four first order differential equations will be required in order to simulate the system and get its response. Okay, I hope that it is clear. I'll go to the second question. As for the Duffing equation, the frequency of the response is independent of the amplitude of response, depends on the amplitude of response, or none. Okay, so firstly, what is a Duffing equation? So I'll write the Duffing equation as x double dot omega naught square x plus alpha 2 x square plus alpha 3 x cube equals to 0. Okay, this is simply a equation of motion of a spring mass system with spring force as a nonlinear equation. Okay, so this is how it is going to look. So if I want to know the frequency of the response, I just want to know the, like, I don't want the exact equation. Okay, I just want to know whether it depends or it does not depend. So what I'll do, I'll just go by trying x is equals to a1 cos of phi. I'll assume that the system is going to behave in a periodic way. It is going to have a periodic oscillation with an amplitude a1 and cos of phi. This phi is obviously a function of time. For example, let us assume phi is omega t, omega nt plus beta, omega t plus some phase difference. Okay, so if I have x like this, I can put it in this equation, right? From there, I can get the relation, correct? So x dot will be equal to a1 omega cos phi. Oh, sorry, to evaluate x dot, no. sine phi with a minus. And x double dot will be equal to a1 omega square cos phi with a minus. Correct? If I want to evaluate x square, it is going to be a1 square cos square phi. And from the trigonometric identity that cos square x is equals to 1 plus cos 2x divided by 2, I can change it. I can write it like a1 square by 2 into 1 plus cos twice of phi. Correct. Similarly, I can write x cube as well, which will be a1 cube cos cube phi. Right. And by using the expression, I can write it like for cos cube x, I can write it as 1 by 4, 3 cos x plus cos 3x. So I can use this identity here and then I can write it like a1 cube divided by 4 into 3 times of cos of phi plus cos 3 phi. Okay, now I'll just put all these into equation, this equation. This I'm going to put in this equation, this I'm going to put in this equation, and this also. Okay, this is your main equation. Okay, so what am I going to get? I'm going to get minus of a1 omega square cos of phi, right? Okay, then I'll get plus omega naught square a1, yeah, cos of phi. Then I'll have plus alpha 2 into, yeah, expression of x square, which is this one. A1 square by 2 into 1 plus cos of phi. And then I'll have plus alpha 3 a1 to the power 3 divided by 4 into, yeah, to 3 cos phi plus cos of 3 phi. Yeah, okay, which is equal to 0. Okay, now you can see that on the left hand side there are cos phi and cos 2 phi and cos 3 phi. On the right hand side it is equal to 0. Okay, so if we want to equate what the coefficients of cos phi, if we want to equate the coefficients of cos phi, because it will be equal to 0, since on the right hand side the value is 0. So what am I going to get? I'll get a1 into omega naught square minus omega square from these two, and from here there is no cos phi, then we have cos phi over here, and we'll have 3 by 4 alpha 3 a1 cube is equals to 0. Correct? So if I take a1 common, which is a1 into omega naught square minus omega square plus 3 by 4 alpha 3 a1 square is equals to 0. Now there are two possibilities. Either a1 is equal to 0 or either this whole expression is equal to 0. So can a1 be equal to 0? Definitely it can be 0. But if a1 is equal to 0, it means that our system is at an equilibrium condition. The system is not oscillating. Okay, but I have assumed that my system is oscillating. Okay, so if my system is oscillating, which means a1 cannot be equal to 0. So what do I get? I get that omega naught square minus omega square plus 3 by 4 For 3, a1 square is equals to 0. Isn't it? From here, I'll get the expression omega square is equals to omega naught square plus 3 by 4 alpha 3 a1 square. So what does this expression tell me? Okay, I have written omega naught here. Okay, so your omega naught is equal to omega n. Okay, yeah. So it means that this omega, which is the frequency of the response, is dependent on our amplitude. Can you see it? If a1 is going to change, omega is going to change. Though if I talk about this expression is not the correct expression. Okay, it's an approximate expression. If you take further components, further series in this, like here, this solution that I've assumed, it's a truncated Fourier series. Okay, if I take more components over here, then I'm going to get different equation. Okay, the equation would be different, but you'll observe that in every case, omega will be dependent on A1. While in case of Ankit Patel, why are you sharing this file in the chat? Okay, whatever. So we'll just see that in this case, omega is dependent on A1. So for this question, which says that for the Duffing equation, the frequency of the response is independent of the amplitude of a response, depends on the amplitude of the response. So correct answer would be it will depend. Okay. I hope that it is clear to you all. If you will have any question, then please ask. Okay. Now coming on to the other question. For the forced Duffing equation, use harmonic balance to obtain relation between the frequency and amplitude. Now what is a forced Duffing equation? It's very simple. The expression that I have shown you here, the Duffing equation. In case of forced Duffing equation, here there will be a forcing term. Okay. So we'll just see for the forced Duffing equation. So I'll assume the equation as x double dot plus x plus beta x cube is equals to f cos of omega t. Okay, so here I have considered the nonlinearity as x cube. Okay, I can consider x square also. I can consider only x square also. I can consider x to the power 5 also. It depends. Okay, but for now I have considered x cube for easy computation. Okay, so now I'll consider the solution. So how is the system going to behave? See, the system is going to behave here. The system is not damped and it is having a forcing. Correct. So if the system is not damped and it is having a forcing, what does it mean? It means that it is going to have a periodic response corresponding to the natural frequency of the system plus the periodic response which is due to the forcing function. So I'll assume that the initial condition that I've given to the system is equilibrium state, 0, 0. So then what is going to happen? See, for a spring mass system, if it is in equilibrium, is it going to oscillate on its own? Never. Till you have not given any perturbation to the system, it is never going to oscillate on its own. Okay, so what is going to happen if I give it some perturbation? Okay, from the equilibrium state, I stretch the mass like this, then it is going to oscillate at what frequency? Definitely the natural frequency of the system. Okay, it is going to oscillate with its at its own natural frequency, omega n. Okay, so and now if that mass is having a forcing, sinusoidal forcing with a frequency omega. So now what is going to happen? It is going to have two components. One is due to the natural frequency and second one which is due to the forcing. Now if it is at an equilibrium state and now I give it some forcing F cos omega t. The periodic oscillation which is due to the natural frequency of the system, that is not going to play a role, isn't it? Only if I give it a certain initial condition, then only it is going to have that component. Otherwise, it is going to oscillate because of it, the forcing function. Also, if the system is going to have damping, in that case, it is going to oscillate at omega only because it is going to have two states of vibration. One is the transient state and second one is the steady state. In the transient state, the omega n component exists, but as the damping, it damps out the vibration due to omega n, and only the vibration which is due to the forcing function is going to exist. Okay, so for now, I'm going to assume that it is going to oscillate at a frequency of omega, which is the forcing frequency. So I assume the solution is a cos omega t plus b sine omega t. Okay. Now if I have x, I can find out x double dot and I can find out x cube as well. So in order to find x double dot, I'll first find x dot, which is what? A omega with a minus sine of omega t plus b omega cos of omega t. Similarly, I can get x double dot as minus of a omega square cos of omega t minus b omega square sine of omega t. Is it fine? Next, I'll have x cube. X I can write like this. I've assumed already. Now I have to find x cube. So x cube would be a cos omega t plus b sine omega t whole cube. Okay, so by the relation a plus b whole cube, we can find out that it will be a cube cos cube omega t plus b cube. Okay, I'm using a plus b whole cube is equals to a cube plus b cube plus 3 a square b plus 3 a b square. Okay, so I'm going to get b cube sine cube omega t. Then I'll have 3 a square b cos square omega t sine omega t, and I'll have plus 3 a b square cos omega t sine square omega t. Okay, clear? Now, if I'll use the trigonometric functions, like for example, if I'll use that of cos cube omega t and of sine cube omega t. I'm not explaining every these formulas because I'm assuming that you people know it. And if in any case you have any doubt, you can ask in the next class. But for now, I'm not expanding and telling that how it is going to come. I'll just write the final what I'm going to get. It will be 3 by 4 a square plus b square cos of omega t plus 3 by 4 b a square plus b square sine of omega t, okay, plus something into cos 3 omega t plus some constant into sine of 3 omega t. So up till now, you people must have understood that we are using the harmonic balance method. What we are doing is we are using the harmonic balance method, and for now we are neglecting the third harmonics. Okay, we are neglecting these because we are assuming that the harmonic are dominant. Okay, these terms are dominant than these terms, so that is why for now we are neglecting these effects and we are considering that it is showing periodic oscillation with a frequency omega. Okay, so now I can write the expression as minus of a omega square sine of omega t minus of b omega square. Okay, here it will be cos and here it will be sine of omega t. Then we are going to have, this is due to the acceleration. Okay, then we'll have a cos omega t plus b sine omega t. This is due to x. Here we have this x. Now we have beta x cube plus beta into x cube, which gives us 3 by 4 a into a square plus b square cos of omega t plus 3 by 4 b into a square plus b square sine of omega t. And for now, I'm neglecting the third harmonics. Okay, and this will be equal to f into cos of omega t. Now, if I use the harmonic balance method by using the harmonic balance method, what are we going to do? We are going to equate the coefficients of sine omega t in the LHS, or we'll just write it oblique cos of omega t is equals to coefficient of sine omega t cos of omega t in the RHS. Okay, so if you will see in the on the right hand side, we only have f cos omega t. We don't have any term of sine omega t, which means that the coefficient of sine omega t on the right hand side is equal to 0. So we'll first do that. We'll first write the sine term. So we have this minus of b omega square. Then we have here plus b. Then we have here, which is plus 3 by 4 beta into b a square plus b square is equals to 0. Just recheck. Okay, minus of b omega square plus b, and we'll have 3 by 4 b into beta a square plus b square. Correct? Now I'll equate this we get by equating coefficient of sine of omega t. Now if I'll equate the coefficients of cos of omega t. So in case of cos omega t, we have a coefficient capital F, which is the amplitude of the forcing function on the right hand side. Okay, so what am I going to get? I'll have this minus of a omega square, and I'll have this plus a. So minus of a omega square plus a and plus 3 by 4 beta a square plus b square is equals to f. See, 3 by 4 3 by 4 beta A into A square plus B square. And this I get by equating the coefficient of cos of omega t. Okay, now if I see both these expression, I can write this expression by taking b common in the first equation and a common in the second equation like this. B into 1 minus omega square plus 3 by 4 beta a square plus b square is equals to 0. And the second one is going to be a into 1 minus omega square plus 3 by 4 beta a square plus b square is equals to f. Now, if you see both these expressions, let's first discuss about the first one. Okay, so yeah, so for the first one, we can see that there is a multiplication here, right? There is this multiplication, and this is equal to 0. Now, this term equals to 0 means either b is equal to 0 or this whole goes to 0. Okay, so we'll have two cases if b is equals to 0 and if this whole term which is into the square bracket is equal to 0. Now, if you'll see the second equation, the term that is in the square bracket is the same as that of the first equation. So, if this term inside the square bracket is 0, then this expression is wrong. If I assume that this is equal to 0, so this is not possible. This is not possible. If the system is oscillating, this is not going to happen. So, then what is the probable solution? This one. B is equal to 0. Okay, so if B is equal to 0, then what can I get? From this expression, I'll put B 0. Right, what am I going to get? I'll get A into 1 minus omega square plus 3 by 4 beta into A square is equals to F. Isn't it? If I put B is equals to 0, this is what am I going to get? 3 by 4 beta into A square is equals to F. Okay, so from here, I can find an expression of omega in terms of A. Also, if I want to find that how the system is going to behave, I can get it from this expression. Now the question is how. So if the system is oscillating periodically, I know the value of this forcing function. I know this value. I know the value of omega. This I know. This is not 0. This is, I know. Okay. So then I can find this A, isn't it? It's an algebraic equation. It's a polynomial. You can find it. Third order. You can find it. Either you can find it on your own or you can use MATLAB also. But there is one thing that is important to notice, and that is that for a particular value of f and omega, there may exist three values of A, which is the amplitude. What does this mean? This means that if my amplitude and omega are both the same, it may happen that depending upon some other parameter, the amplitude by which it is oscillating, the system is oscillating, can have three different values. Is this the case what happens in a linear system? Never. This is never going to happen in a linear system. In a linear system, for a particular value of f and omega, whatever be the condition, it is always going to oscillate at the same amplitude. isn't it? But in this case, that is not same. It is going to have three different values, isn't it? So then what is this? Well, this is what we call the jump phenomena, wherein what happens is that as omega increases, it may happen that its oscillation amplitude increases. But after a certain point, what is going to happen? It is going to fall down. It is going to fall down. How is it going to fall down? It is going to fall down like this, catastrophic, catastrophically, like this. From this value, a small change in omega would lead to this. And this is known as jump phenomena. And this is the reason why it occurs. This expression is going to tell you because it has three values. Essentially, the curve goes like this. This is the unstable branch, which means that the system is never going to attain these value of amplitude. Here, if you'll see a section over here, you're going to see that for this particular value of omega, so let us say some omega 1, there are three values of A. Okay, and this expression is going to give you that. Is it clear? Do you have any question? Okay. For now, I have considered that there is no damping in the system. But what if there is damping in the system? The equation is going to change. This equation of motion is going to change, correct? So let us assume that now the equation of motion, the new equation of motion, which considers the damping. So the new equation of motion, which considers the damping, what would it be? Simple. Here will be a term, psilon x dot is equals to f into cos of omega t. This is going to be my expression with a damped system. So for a damped system, if I have this, then in that case, if I again assume the solution as x is equals to a cos of omega t plus b sine of omega t, what is going to happen? Nothing much difference. Whatever the mathematical analysis we have done previously, only there are going to be two terms added, which is due to this. Correct. Okay, so I already have the expressions. I already have that x dot is equals to minus of a omega sine of omega t, and I have b omega cos of omega t, and I have x double dot as minus of a omega square cos of omega t, and this as minus of b omega square sine of omega t. Only this expression will now be used. In the previous case, when I didn't consider the damping, this was not used. Now this will also be used, and it will come into the equation of motion. So if you remember this previously, what I did, this was my equation of motion. Now what is going to happen? Before this, I'm going to have two terms. I'll have two terms, correct? Which will be, see here, what are these terms? This minus of a omega sine of omega t. Here it will be minus of epsilon a omega sine of omega t, and coming on to the second one, which is plus b omega cos of omega t. So here I'll have plus epsilon b omega cos of omega t. and this will be equal to this. This is the only difference that is going to take place, isn't it? Any doubts? Okay, so now if I equate, I'll just name it as the new equation. Okay, now if I equating the coefficients of sine omega t and cos omega t of the new equation, comma, we get what? Initially I got this expression by equating the coefficients of sine omega t. Now you can see that there is this introduction of one new term related to sine omega t. So in this expression where I had the coefficients of sine omega t, there will be addition of this term as well, which is minus of epsilon a omega, isn't it? So now this new expression will become what? Minus of b omega square plus b plus 3 by 4 b into beta a square plus b square and minus of epsilon omega a is equals to 0. Correct? And coming on to the second one, which was this expression, here also you can see that we have the introduction of one new term which relates to cos omega t. So here where we equated the coefficients of cos omega t, we'll have one more term here added on the left hand side. Okay, and so it is going to give me what? It is going to give me minus of a omega square plus a plus 3 by 4 a beta a square plus b square, and here I'm going to get plus epsilon omega b is equals to what? F, isn't it? This is what am I going to get? See here it is plus and here it is minus. We are going to get with a minus and with a plus. So these are my two new expressions. Okay, now I'll again take a and b common and I'll try to write it like I did in the previous case. Maybe I'll get some solution. So I have b common and then I have 1 minus omega square plus 3 by 4 beta a square plus b square, and then I have minus epsilon omega a is equals to 0. And the second expression gives me a into 1 minus omega square plus 3 by 4 beta a square plus b square plus epsilon omega b is equals to 0. Oh, sorry. It is going to be F. Now I have again two expressions. See, in the previous case, when these two terms were not there, I got that b was equal to 0 and then I could find a relation of a with omega and f. So finding a solution was easier for me. But now I am not getting any such kind of equation. So what am I going to do? I'll try some mathematical manipulation. Now, if you people remember that for an expression a cos of omega t plus b sine of omega t, we could write it like something like c into sine of omega t. Sorry, here it will be plus phi. You can write it like this, isn't it? And there c would be equal to under root of a square plus b square. This comes from the very basic understanding of sine and cosine functions. Okay. So if I have the solution in this form, the way I have assumed it, this is my solution. So it can be written in this form. Okay, I can write it like C sine of omega t plus phi, where I can find the value of C and phi by these A and B. Correct. So now I'll just square both sides of the equation and add it. What am I going to get? Okay, firstly, I'll look into this one. For both first and second equation, the expression inside the bracket is the same. Yes, and we are having a whole square. So what is a whole square going to give me? Square of the first term plus square of the second term minus twice of first term into second term. So for now, I'll assume that this thing inside the bracket is A, B, C, D. Let us assume it as D. I'll just write D because the expression is the same. So what am I going to get? I'll get B square into D square plus epsilon square omega square A square minus twice of epsilon omega A BD. Correct? On the left hand side. Then I'll have plus A square D square plus epsilon square omega square B square. Yeah. Oh yeah, it's fine. Okay. And plus twice of epsilon omega B A into D is equals to F square. Now these two terms are going to get cancelled. Correct? Plus and minus. I have these expressions. I'll have D square into A square plus B square. I'll have plus epsilon square omega square into A square plus B square, which is equal to F square. Okay, so I assume A square plus B square as assuming A square plus B square as gamma square, because anytime I can write the solution in this form. Okay, so I'll assume it as gamma square. So then I'll have the expression as gamma square into D square plus epsilon square omega square is equals to F square, isn't it? Now if I'll expand D again, then I can write it like gamma square into, what do I have here? This 1 minus omega square plus 3 by 4 into beta into A square plus B square whole square plus epsilon square omega square is equals to F square. Isn't it? This is the expression that I got. So now I can find, the relation, no? This A square plus B square will also be gamma square. Now if you see, I have a relation between omega, gamma and F. So if I know F and if I know omega, I can find the value of gamma, isn't it? And if I can find the value of gamma, then I can find that how the system is going to oscillate. I'll know the amplitude of oscillation, right? So then again, I can plot for a given value of epsilon, for a given value of f, and for a given value of beta. I can definitely plot gamma versus omega from this expression. Okay. And by getting this, I solve the question as well. Okay. So if you want, you can go and practice on your own that for the changing for you take assume some values of epsilon, f and beta, and then you plot for changing values of gamma, you plot omega, you plot gamma and see what is happening. See what you can see. You're again going to see that there is a occurrence of three equilibrium state for particular values of omega, which results in the jump phenomena. Okay, so I hope that this question is clear. We have to find the relation between the frequency of an amplitude, and we have found the relation between the frequency and amplitude both with damping and without damping. Okay, what we have done, we have assumed a solution. We use this in the main equation, and then we equate the coefficients of sine omega t as well as cos omega t in order to get the relation between here relation between A and F in case of undamped system, and relation between gamma and omega in case of a damped system. I hope that this is clear. Coming on to the fourth question. Okay, so the question says that which of the following statement is incorrect. So we have to find that which of the following statement is incorrect. So the first is, in the straight forward expansion, the response is expanded by the use of bookkeeping parameter. So what happens in a straight forward expansion is, we assume that for a given differential equation, x is equal to x naught plus epsilon x1 plus epsilon square x2 plus like this, or we can also assume it like epsilon x1 plus epsilon square x2 plus epsilon cube x3 like this, where epsilon is our what? It is our bookkeeping parameter, no? Okay, so and this is what we do in order to solve the equation of motion. So the statement says in straightforward expansion, the response is expanded by the use of bookkeeping parameter. So this statement is correct, isn't it? The statement is absolutely correct. Okay. Now coming on to Lindstedt Poincare method. So it says that in the Lindstedt Poincare method, only the frequency of the response is expanded using the bookkeeping parameter. So in the Lindstedt Poincare method, so in case the Lindstedt Poincare method is a method which is above this straightforward expansion. What do we do there? We assume that there exists a tau, which is a non-dimensional time, which is written as omega t, right? And then what do? We expand omega. Okay, we expand the frequency omega by using the bookkeeping parameter. We define omega as omega naught plus epsilon omega 1 plus epsilon square omega 2. Likewise, we expand. Okay, so up till now, the statement seems correct. But there is one thing which is to be remembered, that it is something which comes after the straightforward expansion. Okay, so what do? Is we still consider the response in terms of the bookkeeping parameter, which means that in Lindstedt Poincare section, Poincare method, what do we do is we assume this, we assume omega in an expanded form in terms of the bookkeeping parameter, but we also assume that x is also written in the expanded manner itself, which is this. Okay, we use all these three things in the Lindstedt Poincare method in order to find the solution of the system. So the expression, the statement that says that only the frequency of the response is expanded using the bookkeeping parameter. So this is an incorrect statement. So this is the right answer. Apart from that, there remains two more options where the third option says that in harmonic balance method, the harmonics are balanced to get the solution, which is correct. That is what we do in the harmonic balance method. That is what we did in the previous question as well. What did we do? We assumed the solution. We assumed the periodic solution by using the truncated Fourier series. We assumed the solution. We used that solution to put in the differential equation. And after that, we try to find out the expression of the amplitude of the oscillation so that we can write it in an analytical way. Okay, so the harmonics are balanced. What do we do? After putting the solution, what do? We balance, we check the coefficients, we check that the coefficients of sine omega t or cos omega t on the left hand side is equal to the coefficients on the right hand side. And from there we get the expression of a and omega. Correct. So this is a right statement. Now the fourth statement says that all the above mentioned methods give the exact solution of the nonlinear system. So what do you think that whether it is right or wrong? Anyone? Okay, so this is a wrong statement. By using all these methods, see in the first two method, what we do? We consider this kind of sorry, yeah. We consider this kind of an expanded form of X, right? Where epsilon is a bookkeeping parameter and it is less than 1. Okay, so what do we get? That the dominance of x dot in the expression is much higher than that of x1, and the dominance of x1 is higher than that of x2, because as the power of epsilon, which is the bookkeeping parameter, is increasing, its effect on the system is decreasing. So what are we doing? We are reducing the nonlinear effect into the system by these kind of an expansion. So it is not going to give me an exact solution of the system. It is going to give me a approximate solution of the system. Okay, and it is going to be correct only up till a certain limit of x. It cannot counter, it cannot tell me about all the behavior of the system, all the nonlinear behavior. Similarly is with the case of Lindstedt Poincare method as well. Here also we are assuming x and omega like this. We are assuming that x in an expanded form with the bookkeeping parameter, and then we are also assuming omega also has a expanded form of with the help of a bookkeeping parameter. So it is also going to give me only the approximate solution. It is not going to give me the exact solution of the system. Okay, by exact solution, what I mean is the closed form solution. Like in case of an linear system, in case of a spring mass system or a spring mass damper system, linear system, I can use the idea of complementary function and particular integral, and then I can properly write x as a function of t. Right, but in this case, that is not going to happen. We are finding the solution only for a certain parameter value and only for a certain range of x. Okay, it is not going to take care of all the nonlinear behavior of the system. Coming on to the harmonic balance method, here we all assume here we assume that the response of the system is periodic. Although you have seen, and I have also tried to make you understand through the simulation, that the response of a system could be quasi-periodic or chaotic as well. So how can we assume that the response of the system is always periodic? It may go into chaos, it can show quasi-periodicity. How would I know? But in case of harmonic balance method, I assume that this response is periodic. Okay, so this also gives me an approximate solution. This is only going to be applicable for the set of parameter values and which the set of initial condition for which the system is going to have a periodic behavior or a periodic solution. Okay, I hope that it is clear. So the answer of this question would be B and D. Coming on to the next question. Okay, so it says that the equation of motion of a system is given as the expression is given with the forcing of sine of 2t. It has damping as well and nonlinearity in terms of x cube. Okay, so which of the following statement is correct if harmonic balance method is applied with the solution assumed as x is assumed as a naught plus b1 sine of 2t. Okay, so we have to find that which is correct. Now, if you see that it has in the question, I have that x is equals to a naught plus b1 sine of 2t. So what do I have to do? I have to evaluate x double dot, x dot, and x cube in terms of this. And then what am I going to do? I'm going to apply the harmonic balance method. I'm going to equate the coefficients of sine omega t and cos omega t on the right hand side and left hand side, and that is going to give me some expression. Let us see. While solving, we'll get to know that up till which expression do I have to go in order to get the expressions. Okay. So, as given in the question, we have x is equals to a naught plus b1 sine of 2t. Then we have x dot as minus, okay, no, minus b1 2 cos of 2t. Similarly, x double dot will be equal to minus of 4 b1 sine of 2t. Fine. Coming on to x cube, which would be equal to a naught plus b1 sine of 2t square. Yes. So what is it going to give me? It is going to give me a naught cube b1 cube sine cube of 2t plus twice of a naught square b1 sine of 2t plus twice of a naught b1 square sine square of 2t, isn't it? Now I can use two trigonometric functions, identities, I would say, which says that sine square of x is equals to 1 minus cos of 2x divided by 2. This is the first one. Second one is going to be sine cube of x is equal to, here it will be 4, 3 times of sine x minus sine of 3x, isn't it? I can use this, right? So I'll put these in the above expression and then I'll get x cube as a naught cube plus b1 cube by 4. I'll have 3 sine x minus b1 cube by 4 sine of 3x. Then I have twice of a naught square. See, here I have done a mistake. Here it will be 2t and here it will be 60, isn't it? Then I'll have sine of 2t. Then I'll have plus a naught b1 square. Okay, since this 2 and this 2 will get cancelled, I'll have a naught b1 square and then I'll have minus of a naught b1 square into cos of 40 from here, isn't it? So I'll use this expression. this expression and this expression in the equation. So what am I going to get? Okay. So see, first I'll have to write x double dot, which is minus of 4b1 sine of 2t. Then I have 0.1 x dot. So 2 into 0.1 would give me 0.2. So I'll have plus 0.2 b1 cos of 2t. Is it fine? Multiplying this by this 0.1. Okay. Then I'll have x. X I know what it is. It is plus a naught plus b1 sine of 2t. Then I have 0.2 x cube. I have plus 0.2. Now see, this x cube expression is going to give me both the expressions which have sine 2t and and there is also sine 60 and cos of 4t. Okay, so we know that we are going to apply the harmonic balance method in order to find the coefficient relation of the coefficient. So for now, I'll neglect sine 60 and cos 4t. Okay, I'll consider just sine 2t. Okay, and the constants, these values, which does not have sine or cos multiplied with it. So what am I going to get? 0.2 into a naught cube plus 3b1 cube by 4 into sine of 2t. Then I have twice of a naught square b1 into sine of 2t. And then I have, sorry, plus a naught into b1 square. Correct? So this is what am I going to get? And this is equal to what? 0. Okay, 1 into sine of 2t. Now I can equate the coefficients, isn't it? Now I can equate the coefficients. So first I'll equate the coefficients of, or I would say that I'll equating the constant terms. What is going to happen? A naught, then I have plus 0.2 a naught cube, and then I have 0.2 a naught b1 square is equals to 0. So is there this in the option? A naught plus 0.2 a naught cube plus 0.2 a naught b1 square. Yes. So this is the correct answer, isn't it? I got this by equating the constant terms. Apart from that, if I equate the equating the coefficients of sine of 2t, what am I going to get? See, sine 2 is here, so I have minus of 4b1, sorry, then I have it here, gives me plus b1, then I have it here, which gives me plus 0.2 into 3 by 4, which would give me 3 by 20, isn't it? 3 by 20 b1 cube, and then I have here, which would give me plus 0.4 a naught square b1. This is equals to 1, isn't it? So I guess this is what is going to give me my second correct answer, which is minus 3b1. Then I have plus 3 by 20 b1 square, sorry, b1 cube. And then I have 0.4 a naught square b1 is equals to 1. Is it there in the option? Yes. So this is also my correct answer. So I hope that this made you understand that how do you have to work on the harmonic balance method in order to find the expression. See, I have done the equating of the coefficients only in order to find the answer of this question. You can see here that if I see the constant, the coefficient of cos 2t, there is only this term, and this will be equal to 0, which will give me the value of b1, which will be 0. Now, if I get the value of b1 as 0, then I can further find the value of a0 and a1 as well. Okay. It may happen that this may get me wrong answer, which is because I have considered the solution like this as a truncated Fourier series. If this gives me a wrong answer, then I'll have to consider maybe a1 cos of 2t, and then I'll have to consider a2 cos of 4t plus b2 sine of 4t. Likewise, in order to improve the accuracy of this approximate solution. Okay, I hope that this question is clear to you all. Coming on to the sixth question. Okay, so the sixth question says that the Lindstedt Poincare method gives the following equation for a system. We have two expressions. Okay, then which of the following is correct by which secular term is avoided? Now, what is a secular term? Okay, I'll only tell what is a secular term. So, a secular term essentially means that a term which goes to infinity as time increases. Okay, so if I consider this first expression, in order to find x2, what will I do? I'll integrate it. I'll find the complementary function and particular integral, which is fine. Now, if I see this, if I find the, if I want to find the complementary function, I'll equate this to 0 as of now. So it would give me plus x2 is equals to 0. I can also write it as d square plus 1 into x2 is equals to 0. From here, I can get the value of d, and then I can write the complementary functions like c1 e to the power. What am I going to get? I'm going to get this will be I, right? Iota. D is going to be, d square is minus 1, so d is going to be plus minus I, isn't it? So what will it give me? It will give me the response of the system. I'll write the response as c1 e to the power minus of it and c1 e to the power plus of it like this. Sorry, c2. So I get the complementary function. No problem if the roots that I'm getting is what? Just a second. If it is complex, then this means that the system is going to oscillate. Okay. So for that, the system is oscillating. Now coming on to the particular integral. So in order to find the particular integral, if I talk about this first expression, how can I find the particular integral of this expression, of this term actually? So what am I going to do? So the way the formula says that if I have some trigonometric function like sine or cosine over here, what will I do? I'll write the particular integral like minus of 2 omega naught omega 1 cos of t divided by d square plus 1, which would be this function. Okay, now then what I have to do? Like for example, if I have sine of ax on the right hand side. Then in order to find the particular integral, and here I have the function of d. Okay, what do I do? In this case, I replace d square by minus of a square. Okay, and then I replace this here, and then I get the particular integral. But what if after, okay, wait, f of d is equals to 0 when d square is replaced by minus of a square. This will become 0. It will become an undefined value. Okay, so then what do we do? What we do is we differentiate this, we write, and then we write the complementary function as, here we multiply the numerator with x, then we write sine of ax, and in the denominator what do? We find f dash of d and then we replace d. Okay, so in this case, and this is also provided that f dash of d does not get to 0. If gets to 0, then we'll go for the second differential, and on the numerator we'll multiply by x square. Okay, so if you will see for this expression, here what do we have? Here our a is 1. So what do we have to do? We'll have to replace d square by minus 1. And if I do it here, what is going to happen? Minus 1 plus 1, 0. This becomes undefined. So in that case, I'll have to multiply it with t over here in order to find the particular integral, isn't it? So in order to find the particular integral, the numerator is multiplied by t. Okay, no problem. It gets multiplied by t. I'm going to have the particular solution, a particular integral like this. But is it correct? Never. The system is bounded. The system is going to oscillate. What that means is, if the system is bounded, it is never going to go to infinity. Correct. But if this t is multiplied over here, if minus of 2t, if this t is multiplied over here, then what is going to happen? As t tends to infinity, my x2 is going to go to infinity, which is not correct for a bounded system. The result has error. It's a blunder actually. Okay, so in that case, what do? We say that these kind of terms are known as secular terms, and these secular terms need to be avoided, which means that this should go to 0 in any case, because the system is bounded. It is always going to oscillate. It is never going to go to 0. Okay, so which means that this term is supposed to be 0. In order to avoid the secular term, we say that this is 0. So twice of omega naught omega 1 cos of t is equals to 0. Sorry, cos of t will not be here. Only the coefficient will be equal to 0. So this is equal to 0. Now when is it going to be 0? It is going to be 0 only if omega naught is 0 and omega 1 is 0. Correct. Now we know that omega naught is not equal to 0. We know that for sure that omega naught is not equal to 0. Isn't it? Omega naught is not equal to 0. That is for sure. So then what is the probable answer? Omega 1 is equal to 0. So in order to avoid the secular term, in order to avoid the error in the answer, in the approximate solution, or in order to avoid that a system, how is it is going to behave, we say that omega 1 is equal to 0. Correct. Just a second. Okay, omega 1 is equal to 0. So if I see in the question, omega 1 is equal to 0, which of the following is correct by which secular term is equal? So omega 1 is equal to 0. A is the correct answer. Now coming on to the second expression. So if you will say in the second expression, do I have any secular terms? Okay, so see here, again we have cos of t. Oh, sorry, I'll just take this first. See here, we have 1 plus cos 2 times of t. So when here is 1, we consider it as e to the power 0 case. It is not going to be a secular term. And coming on to this cos of 2t. Here our a is 2. Here our a is 2. So what is going to happen? We'll have to replace d square by minus of 4. So in the denominator where I was having d square plus 1, I'm going to have now minus 4 plus 1, which is going to give me minus 3, which will not make the system, this will not make the system undefined. So there is no need to differentiate in the denominator and multiply the numerator by t. There is no need. Okay, it is just going to give me the term which will not go to infinity as time goes to infinity. Coming on to the second expression, as you can see that here we have cos t. Now in the previous case also this cos t was creating problem. Here also this is going to create problem because here also if you'll see we have the same expression. Okay, so here it will not be 2, it will be 3. Okay, so here also we'll see that our expression will be d square plus 1. It is going to be d square plus 1. Again, we have to avoid anything that has 1 here. Omega should not be equal to 1. So this is my secular term. So this should be equal to 0 in order to avoid infinity. So I'll have, what is the expression? Omega naught omega to a, omega naught omega to a. I have minus 3 by 8 alpha 3 a cube minus 3 by 8 alpha 3 a cube. Then I have plus 5 alpha square a cube plus 5 alpha square a cube. Here it will be alpha 2, I guess. Yep. 12 omega naught square. This will be equal to 0. Omega naught omega 2 a. Then we have minus 3 by 8 alpha 3 a cube plus 5 alpha 2 square a cube. This is equal to 0. This should be equal to 0 in order to, why this should be equal to 0? In order to avoid the secular term. So what would this give me? Omega 2 I can write in terms of omega naught and alpha 2 and alpha 3 and a, isn't it? I can write it. How am I going to write? Omega naught omega 2 a is equals to 3 by 8 alpha 3 a cube plus 5 alpha 2 square a cube omega naught square. So as you can see, I have a cube a cube. So I can use this in order to get the expression. Okay, so what is going to happen? Okay, are you able to see my screen? I guess my screen got frozen. Can you see what I am writing? Okay, I'll just check for once. Okay, now it is visible. Okay, okay. So I have A common on the LHS and RHS. So I'm going to take it out, and then I can write omega 2 as 3/8 omega naught alpha 3 a square, and then I'll have plus 5 alpha 2 square a square divided by 12 omega naught cube. Correct? I can further write it in this way as well. If I take, like it is written in the answer, if I take denominator as this, then what is going to happen? And I take a square as common, then I'll have 9 alpha 3, I'll have 10 alpha 2 square, isn't it? Oh, I'll get a, okay, fine. Here there's going to be a minus as well because it is coming on the right hand side. So it is going to have a minus as well, and it is going to have a omega naught square as well. So this is my expression that I'm getting of omega 2, for which I'll avoid the secular term in case of the third x. Okay, so this is what am I getting. So these are going to be my correct answers, A and C. And anyways, D is also correct. Okay, I hope that this is clear. Now coming on to the seventh question, which is a MATLAB based problem. So I'll just switch to my computer now. There are only two questions left. Okay, so I'll just connect with my computer. Okay, I hope that my screen is visible to you all. Okay, thank you. So coming on to the seventh question. So the Rayleigh equation is given as, here's the expression. So which of the following option is correct about the steady state response of the system for initial condition 1, 1 and 2, 2. So first of all, what is a steady state response? Simple, when the system settles down to a current to a position. If there is damping present in the system is going to show, like in case of spring mass and damper system. So, and also if we have the forcing present in it. So what is going to happen? If I give any kind of initial condition along with the forcing function, it is going to show some transient response, and then it is going to settle down, okay, to a maybe a periodic response, quasi-periodic, that would depend upon the parameter values, okay, but it is going to have two responses, transient response and steady state response. So this question says that for the Rayleigh equation, if I consider two initial conditions, what is going to be the response of the system? And here are the four options. So I'll go to the MATLAB. Okay, again, if you'll see here, I have written the equation of motion like this. Okay, so what is happening in the equation of motion is, first, okay, the same concept comes that I have a second order differential equation. What am I supposed to do? I have to convert that second order differential equation into two first order differential equations. Okay, so I'll write it in this form. I'll write Z2 and Z1, where Z2 is my velocity, isn't it? Z2 is my velocity. So the first is the velocity. So integration of velocity would give me the position, and the second is the acceleration. So the integration of acceleration is going to give me the velocity, and only the position and velocity is the thing that I want, because acceleration expression I already have, so I can take it out anytime. Okay, so I have minus of Z1, like in this case, if I bring all these terms on the right hand side, what is going to happen? It will have minus of u plus u dot, and it is going to have minus of u naught cube. So here you can see plus of u dot and minus of u naught cube, and EP is divided by it. So here in the expression, EP is given as 1. Again, I'll simulate the system from 0 to 20, and I've taken the initial displacement as 1 and initial velocity. Okay, I'll just write it for you to understand that initial velocity is equals to 1. And I'll just use this expression instead of writing 1 here. It will be easier to understand. Initial underscore velocity. Okay, so I define z dot I like this, and then I give the OD45 command. Okay, so I'll just simulate the system and see what is going to happen. So figure 1 gives me the time response, and figure 2 gives me the phase plot, which is the, so here this is time x-axis and this is your u, and here x-axis is your u and y-axis is your u dot. So you can see what is happening to the system. The system started from here, which is the initial condition, and then it came to this, follow this periodic loop. Okay, so this is the response of the system. Now what is the second set of initial condition? 2 comma 2. So I'll just change the initial condition to 2 and 2, and I'll see what happens. I'll run the code, see what happened. Though the initial condition has changed, the system still came to the same periodic loop. Okay, now you can see the phase plot and time response as well. You can see that there is, but in the time response, you can see that there is some phase lag. Although the maximum point and the minimum point are the same for the steady state, but there is some phase lag. By phase lag, I mean is that the maximum position of the case where I've considered the initial condition as 1 comma 1, it reaches earlier than that of the case where I've considered the initial condition as 2 comma 2. So there is this phase lag that occurs in the system. Although you can see that in the phase plot it follows the same closed loop. Although their initial, which I would say transient response, is the same. Both is not the same. Both in the time response and phase plot, the transient one is not the same. But after some time, it comes to this, follow this closed loop in order to show periodic oscillation. So I think it is giving me a hint that it is a limit cycle. So I'll just try for some other set of initial condition as well, whether it is going to follow the same loop or not. Yes, it is following the same loop. Even if the initial condition is inside the loop, it is again going to the loop, which shows that it is a limit cycle. And also you people must remember that the van der Pol equation comes from the Rayleigh equation, comes from the some method after some mathematical manipulation, we can get the van der Pol equation from the Rayleigh equation, and you all know that the van der Pol equation is famous because of the existence of limit cycle in it, despite of the non-presence of forcing function. The forcing function is not present there, still it shows the existence of limit cycle. Okay, so the Rayleigh equation is also showing the presence of limit cycle. So if I come to the expressions, sorry, options, say the response are different. Okay, this is wrong. The response is same. So this is the correct answer. And if I see the option C, both lead to the same closed loop. This is also correct option. So in this case, we have two correct options. One is that the response is same, and the second which says that it lead to the same closed loop, which is the limit cycle. Okay, so limit cycle has a significant impact in the nature, as most of the natural oscillations, they follow the limit cycle. So this is also the correct response. Even your assignment problems can have a case where there are multiple correct options. So please read the question properly and then attempt it. Okay. Now coming on to the last question. Use the MATLAB symbolic to solve the equation by using straightforward expansion. So coming on to the MATLAB symbolic. So what is MATLAB symbolic? Simple. Instead of specifying the value of a variable in terms of a constant value or an array or a matrix, I want x to be x, like I do. Okay, so in that case, I use symbolic. So again, what do? I just define. So what is the expression? Let me see first. I have x double dot plus a1x plus a2x square is equals to 0. So first I'll have to define the symbolic variables. Okay, so which will be sims. I have x as a function of t. I have a1, I have a2, isn't it? Apart from that, I am using the straightforward expansion in which I'll write the x as epsilon x1 plus epsilon square x2 likewise. So what is epsilon? Epsilon is also a EP. Epsilon is also my symbolic variable. Okay, so I'll write EP. Apart from that, I'll have x1, which will be a function of time. Then I'll have x2, which will be a function of time. Sorry, here it will be t. Yeah. Then I'll have time itself. Okay, so I'll just enter. Okay, so you can see here in the workspace, I've got my symbolic variables. Now what do I have to do? I'll write x, okay, which is my solution. And how am I going to write x? Obviously, I'm going to write x in a expanded manner by the use of the bookkeeping parameter. So I'll write x like ep into x1, and then I have plus, then I'll have ep square into x2. For now, I'm considering only up to second order. Okay. If you want, if you learn that how it is happening, I'm just giving you an example, then you can go and do it on your own. You can consider to the fourth, fifth, or even 10th order because it becomes easy with MATLAB to solve this expression, you know. Solving, when you're solving manually, you can go to third order or maybe fifth order with proper accuracy. But if you want to go till 20th or 30th order, it is preferable that you use softwares like this. Okay, it is going to reduce your time as well and it's going to give you more accurate solutions. So I have assumed x as ep into x1, which is epsilon x1 plus epsilon square x2. Okay, now I'll write the differential equation. Write the differential equation as difference of x comma t. If you remember, it is differentiation of x twice the differentiation of x. Then I have plus a1 into x, and then I have plus a2 into x to the power 2. This is the expression that I got in the PPT. See, x double dot plus a1 into x plus a2 into x square. See, what can you see? Okay, for example, here I have defined my x. Let us do one thing. I'll define sims x again, and I'll write this. Okay, sorry, I did a mistake. I didn't write t here, and that is why I didn't differentiate it t with respect to time. It gave it as a value 0. See, what did I get? I get the expression that is given in the question. Okay, in terms of x double dot and x. But then I assumed x like this. And then I again call this equation. So now what? It gave me the equation in terms of EP into x1 and EP squared into x2. Epsilon x1 in terms of x1 and x2. Okay, now what can I do? Now I'll have to segregate. Segregate the equation in such a form such that I'll have an equation which corresponds to equating the coefficients of EP, which is epsilon, and that of EP square. Okay, so what am I going to write? First, I'll expand it. Okay, I'll write yy is equals to expand DEQ. It expands the equation. Okay. Now after expanding, now what do I mean by expanding the equation? Expanding the equation simply means that instead of x square, it will write the whole expansion of epsilon x1 plus epsilon square x2 whole square. Okay. Now I'll call the collect command collect yy comma ep. What is going to happen? See, it is going to collect the values. Like first it wrote whatever is the coefficient into EP to the power 4. It collected all the values that are related to EP to the power 4. Then it will collect all the values that are related to the power of 3, EP to the power 3. Okay. Now, after this segregation, it will become easier for me in order to take that expression and then find the exact solution. So, it will arrange it in a descending order. So, first comes EP to the power 4, EP to the power 3, then we have EP square, and then at last we have what? EP. Here you can see that. Now, if I see this EP, what it is multiplied with? It is multiplied with a simple equation. So, I can find its solution. See, now I have two options. I can either find it on my own or I can use MATLAB for the same. So what will I do? I'll try to solve this with MATLAB. So I'll define ODE is equals to this. I copied whatever is multiplied with EP. Okay, and I defined ODE with this. Now I'll do what? I want to get the solution. So I'll call the dsolve command. See, it gave me the solution, isn't it? It gave me the solution of the equation. First differential equation that I get in terms of x1. Now I want what? Now I want the expression of x2 as well. If I'll get the expression of x2, then I can write the equation as x1 plus epsilon into x2. Correct? So I can find that. Like I got the answer. Now I'll define x1 is equals to answer. That is my x1. The answer is my x1. Okay. Now I'll replace this in what? In the second expression. No. See. Here where I got after collect, I got this expression which was multiplied with EP square. This was the expression. So I'll just copy this expression for now because this is where I have to solve it. And there's one thing also. Now I'll define the new ODE as this. Okay, and I'll just remove t from here because now my x1 is defined. I have the defined x1. And I'll go for enter. It gives me the ODE. Now I'll again call the resolve and it will give me the solution of this new ODE, which is the ODE which relates to that of x2. Here, I got the solution. See, the solutions are a bit long because I have not defined the answer in terms of sine or cosine. It is dividing it in terms of e to the power. Okay, now I have the expression of x2 as well. So now I can define x is equals to again like ep into x1 plus ep square into x2. So I have to write x2, but here I didn't see, I didn't, when I called the dsolve command, I didn't give it a name. So it came out as answer. So I'll just write ans here. And here I got the expression of, you can see here. Here, what is this? This is my answer. from the straightforward method. You can see how long the solution is. Okay, so this is how you can solve the symbolic functions in MATLAB in order to solve the nonlinear differential equations in order to get its approximate solution. Okay, so yeah, that is it for today. If you have any doubts, you can ask me. Any doubts?
No, madam. Thank you.
Okay, fine. Just go and revise whatever I have taught, and if there is any doubt, you can anyways ask in the next live session. Okay, so I guess this is it for today. Thank you so much.